Good, welcome back. I didn't get as much time as I wanted to prepare slides. So I've got a message to give you, but I might jump back and forth a little bit. Anybody got any questions from this morning? Nope, okay. Yeah, I left off here. Thanks, Gibran, for setting it up. And that's the new version, right?
Yeah.
Okay. Okay, so I mentioned these two algorithms, and I think I'm going to talk more about this afternoon, the quantum simulation. And the reason I'll do it, there seems to be a real interest here in the quantum machine learning aspect, so machine learning. So I'll give some of the backup explaining it, and then tomorrow in the morning session is problem solving, but then the afternoon is another lecture, and I think there I'll go into optimization, variational quantum eigensolver. So tomorrow afternoon, I think I'll talk more about the quantum chemistry type problems that people are interested in. And today I'll just I want to give you the feeling for the linear equation solver and why that's important for machine learning. So I think that's okay, right? So today, linear equation solver, tomorrow, variational solver for optimization. That's the idea. Okay. So then I explained, I had on the board earlier, the Hamiltonian simulation. I have to get this idea across. I was going to try to be a little bit cursory on it, but I think it has to be clear. So as I said this morning, that the program is described by a unitary map. And the physicists will like to think about the Hamiltonian. And in a mathematical sense, just think of the Hamiltonian as a logarithm of the unitary map. That's how it works. And so in order to understand linear equation solver, it's better to think of the Hamiltonian formulation, and you'll see why soon. Okay, this one we don't worry about. There's two different kinds of quantum simulation in the literature. This is the one that, to me, has the real merit in exploring capabilities for quantum computing. The other one is also called quantum simulation. This is, I'll give you an example to tell you how it works. So suppose that you're going to design a new airplane. And then the new airplane, you're designing the wing for the airplane. Well, how do you design a wing for the airplane? When you design it, you'll write into a computer-aided design program, get the wing shape, and then you'll use fluid mechanics to start simulating how it behaves. So you'll do a simulator on your computer subject to equations that describe the physics of what you understand. And then you test it. When you're finished, then you'll build a tiny model of the wing. You'll have a wind tunnel where you blow air through, and then you physically check what's going to happen. So you build a physical simulator that behaves like the airplane wing really going through the sky. So this kind fits more the former, where this is saying we're just building a quantum computer and we're going to simulate on a quantum computer according to theoretical descriptions what's going to happen. And this is the latter, where it says we're going to build a physical system that behaves like the system we want to understand. Okay, this one I won't go into in these lectures. I don't have time. It's got the application for this would be supermaterials. So we have superconductors, superfluids. There are various materials that have macroscopic quantum properties. Those are known as supermaterials. And the argument is that this area is important to check our theories for designing supermaterials. I won't cover it. Okay, so back to this one. Okay, so let's go back to what the Hamiltonian is. And I made some notes based on what I said this morning. So I'm reminding you that a quantum program is really just a unitary map. It's an isometry. It preserves the inner product. And so it just has the property that if you take an input state psi, map it. So this is the input. Once the information goes to the quantum computer, this could be the quantum register storing the input information. This is the computer program, and the output has the same norm as the input. So it turns out that in quantum mechanics, it makes sense that everything has norm 1. It has to be the same before or after. So ultimately, this rule is why it has to be a unitary map. And the norm of the state is the Hilbert space has an inner product, so it's the inner product of the state with the state. And you've learned in other lectures, like the Rigetti one, that the state is just a complex vector. So it's a row vector complex conjugate times a column vector. That's the norm. Okay, that's what it solves. Then, as I said this morning, I wrote on the board, and I just want to make a slide to make it clear. There's Stone's theorem, and actually, I looked up, it's got more than one theorem. So this is Stone's theorem on one-parameter unitary groups, but essentially it just says for every u of t. So this would be a unitary map. Think of it as a program, but think of it as time-dependent. It can depend on something. It can change. There exists a Hamiltonian H equal to H dagger. This is the adjoint. So the adjoint, and now I won't go into the details, but anybody's mathematically inclined, once you have an inner product, the adjoint is just a way of taking operators on the right and acting on the left. So there's some way to define it. In terms of matrices, maybe I'll write this on the board. Hope you can see it. So H equals H dagger. That's the self-employed, the self-adjointness condition implies that the matrix equals the complex conjugate of the matrix transpose. So if we use a matrices for these operators, as you learned in the Rigetti lecture, when I say that it's self-adjoint, it just means that the matrix, if you take the complex conjugate of the matrix and you transpose it, you get the same matrix back. So Stone's theorem tells us that for every unitary, there always exists a self-adjoint operator such that this is true, and that's why I tell you just think of the Hamiltonian as the logarithm of the unitary matrix. Okay, and then the physicist likes it because then in physics, we often like to think of continuous time. There's actually very beautiful work by Michael Nielsen, very well-known quantum information theorist of about 15 years ago. He stepped out of the field now. That he kind of looked at the dynamical flow of quantum computing. So instead of thinking of a program as a sequence of steps, he started thinking of it as a Hamiltonian generated flow. So you can just think of the computer as a machine that's executing a continuous evolution. It leads some very nice ideas. Anybody in theoretical physics might appreciate that that way of thinking has suddenly resurged very fast in quantum gravity work, where people are trying to relate physics to complexity. So if anybody's into quantum gravity, there's a very beautiful way now to connect those ideas. And to a physicist, we write down Schrödinger's equation. Schrödinger's equation can be that there's some quantum state, and its evolution in time is generated by the Hamiltonian. So in some sense, the Hamiltonian is conjugate to time. It generates time evolution. Okay, so that's the idea about the Hamiltonian. And then I thought I'd give you an example. Now this one, I put it up here. I'm going to explain a little bit what's going on. And it relates to the lectures tomorrow on quantum annealing. I hope you can read it. I didn't have time to take out that background. But this is known as the Heisenberg model. And basically, it describes a magnet. So let me try to draw it like this. So what happens is, let's say you take a magnet. Can you see that? Is it visible? Okay. So let's say this is a magnet. What is a magnet? Well, a magnet has just a set of sites. Okay, and so on. And if it's magnetized, you can think of a magnet as having all kinds of little tiny magnets inside. And if they're all aligned the same way, so if they're all the magnets point the same way, then this would be called magnetized. But if it's demagnetized, then they can all point different ways. And this happens if the temperature is high. So you have magnets in some random configuration. Okay, this is actually important. So when I talk tomorrow about the D-wave quantum computer, I'll come back to this point. In effect, those quantum annealer computers that we'll discuss tomorrow are just big quantum magnets. It's just what happens is they have local applications. So instead of everything lines up because you have a giant magnetic field applying to the whole thing, but imagine that you could apply different magnetic fields at different points in the magnet. The final configuration of the magnet is actually the answer to the computational problem, which I'll explain tomorrow. So, so you can think of those things as just big quantum magnets. These things interact with each other. You know, if you bring two magnets together, they try to anti-align. That's what this Hamiltonian is all about. So this Hamiltonian is describing a magnet. This sigma, so the sigma dot sigma is, it's sloppy notation, but it's very common. It's just x tensor x, y tensor y, z tensor z. Now you remember what x is? So x is the not operation, right? So in the Rigetti slides, that's why I reviewed them, it's 0, 1, 1, 0. Okay, what was y? Yeah, 0 minus I? Is that what you said? What? So, okay, is that self-adjoint? Is that equal to y dagger?
The convention was minus on the top. That's like
Minus and this, yeah, good. Z is equal to 1, 0, 0, minus 1, right. And then when you do a tensor product, you get x tensor x is then 0, 1, 1, 0, tensor 0, 1, 1, 0 equals, and then you just have 0, 0, 0, 0, and then is that right? Okay, so then that's all we're doing. We just take those, add them all together for the nearest neighbors, and that's this expression here. Okay, and that's between the I and I plus 1. These are all identities, and it's a sloppy notation, but it's just a way of writing the interactions. So in 2 dimension, this interacts with 1, 2, 3, 4 elements. So when you add them up, you just have the interaction here, here, tensor with identity. This is what we write. And then what you see, so what I've done here is to write it in a 1-dimensional case, not 2-dimensional. And in this case, the idea is to write down the case just for 2 magnets nearby each other, according to that Hamiltonian, write the matrix. And so using this matrix is telling us the interaction. Diagonal elements are on-site energy, the energy of the magnet, and the off-diagonal is how strongly they couple. And then if I go to 3 magnets in a row, what you get, 4 magnets in a row, and you can see the kind of matrix. So this then converts this Hamiltonian to a matrix, and we exponentiate it, right? So this matrix is not the unitary operator, it's the self-adjoint Hamiltonian operator that's exponentiated. Something very important emerges here, and that's that the matrix is sparse. Now, in a strict sense, sparse, when you do computational complexity theory, sparseness doesn't just mean that most of the elements are 0. It means that if you grow the size of your system, you keep going up, the number of non-zero entries grows what's called polylogarithmically in the number of rows. Polylogarithm means that it's a polynomial function of the logarithm. So this 2 elements, there's 2 squared, 4 by 4. This has 1, 2, 3, 4, 5, 6, 7, 8, 2 cubed. This should be 2 to the 4. So the size of the matrix grows as 2 to the power of the number of magnets, but the number of non-zero entries is growing linearly. That D is telling you the maximum number of non-zero entries by row or column. So one of the things you realize when you're doing physics, it's a beautiful property, is that when you start writing down the physics of any system, you discover that when you write it down in the natural way, and the natural way is in terms of energy, it's always a sparse matrix. And that sparseness is important in physics to be able to simulate things. And the sparseness comes up in machine learning with respect to many properties expect sparse matrices, recommendation algorithms, all kinds of stuff. Okay, and I'll mention those. So this is the idea. I just wanted to give you an example of a Hamiltonian. You could see the matrix and see that it's sparse. Okay, and this one will come up again tomorrow in the context of quantum annealing. Okay, just to point out that once you get that, you recognize it's sparse, it turns out that you can replace the matrix by a graph. So let me just explain what's going on here. So if I write the matrix, it's kind of a waste of time. I'm writing a lot of zeros. If I store it in a database on a computer, I'm wasting space, right? So when you do things in computing, you want to find a smart way to store it and a smart way to manipulate it. So I'm just showing you that part of the step that we do, once we demand a sparse matrix, is we don't keep it in matrix form. So what I might do is say, just here's the query. And so I turn into a query problem. And this will relate to oracle problems, oracular problems. So I might say, what is the third non-zero entry? So let's say that's the 0, 1, 2 column. So what is the second non-zero entry of the second column? Because we start with 0. Then I go 0, 1, 2, and that's the entry. You see? So then the way that we set these up are as oracle calls. And the oracle call is saying just order the oracle is able to answer the question about the non-zero entries, and D sets an upper bound. So if you ask for the final one, so it'd be the third, since we're starting with 0, it would then give an answer that would tell you that you've ended the list. But you could get up to 4 non-zero entries, and then you would stop. So your oracle, you store your matrix in an oracle. So an oracle, for those who don't know, is equivalent to a subroutine or subprogram. So you store it in some oracle as a call. So that's what happens. Once you do that, then it turns out that you want to represent it as a graph. And so the graph here would be, this could be row X, column Y1. This weight of the graph edge is the value of the matrix element. So if we go back to here, we could say that we have the 0, 1, 2, 3, 4, fifth row, and 0, 1, 2, 3, third column. So we have the number 5 for the row, the number 3 for the column, and the value of 2 is the weight. That's what's going on here. Okay? 5, 3, and 2 is the weight. And then what happens is we just draw an edge for each non-zero entry in that row. Okay, so here we take a look at the row, and we had 0, 1, 2, 3, 4, 5. We have this, 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 you see? So we need 4 edges from the X. So this is the way that we represent it. For people who know graph theory, this is an adjacency matrix. So that's what we store here. The point is, it's interesting, remember that the matrix is self-adjoint. So if I take row 1, column 2, and then I go to row 2, column 1, I get the same number. So there's a symmetry. So whether it's a row or a column doesn't matter. It's going to be the same. So then the way it works in graph theory is that we don't have arrows on the edges, because the implication of it being self-adjoint is it's an undirected graph. And then what happens is we start to put it all together. So this would be an example of writing a Hamiltonian as a graph. And then we write the Hamiltonian as a graph, and we look at this. This could be the row number, column number, or column number, row number. And then these numbers here are, you can say, what is the first non-zero entry? Now, when you look here, you see a very ordered pattern. It's all ordered. But it could be scrambled. You need to write it. You don't know in advance for a general Hamiltonian how it's going to be ordered. So if I write the oracle or you write the oracle, it might be different by a permutation of the matrix rows and columns. So we need to make sure that when we deal with these, it's independent of the of permutations. So over here, this would be what is the first non-zero column for that row. But if that column becomes the row number, then the number 2 says the second non-zero entry of that column is that row is that column. So there's a slight, we have to be very careful in how we do it. But these numbers are just a way of keeping track of whether it's the first, second, third. And then what happens is when we do that, then we start writing quantum algorithms to simulate. Once we express it in this graph, then in order to execute quantum algorithms, and I won't go in, I'm going to keep it more high level, we then break it up. So basically, each Hamiltonian creates a gate. So in the gate-based approach, the idea is that we have gates. So I gave you H, T, C naught was one case. The other one I gave you H, C, C naught. So when you deal with quantum computing based on gates, which is what Rigetti and other companies, some are aiming for, then we express the gates. If you do it based on a Hamiltonian, what you really want to do is to write this matrix as a sum of matrices that are called one-sparse. Only one element in any row or column is non-zero, and we want to be able to write it as a sum. If we do it, each one-sparse matrix plays the role of a gate. And so here, it's a graph coloring problem. Has anybody heard of the famous 4-color map problem? Yeah. So it's very interesting, historically, mathematics. So it was conjectured that if you draw a map of countries, borders, the belief for a long time, more than a century, was that you only ever need a maximum of 4 colors. And nobody could prove it. And so the proof, maybe 20 or 30 years ago, was the first ever mathematical proof that was done by a computer. And so it's a coloring problem. It's the same thing here. Basically, a one-sparse matrix corresponds to a graph where every vertex has at most one edge. And so what we have to do is write it as a disjoint union of graphs with at most one edge. And the way that we color it starts with, like, the 1, 2 becomes a red-blue color. Here we could have a green-green together. So we have some quadratic overhead. And there's added complications I won't go into. They're interesting. But once you do that, basically you execute a graph coloring algorithm to do this, and then you're able to make the equivalent of gates. Okay, so that's, again, high level, that's the analogy of doing this for this Hamiltonian simulation. Okay. Now, let me go into what we're solving here. So, yeah.
However, to find out the non-zero number, we have to visit every index of the matrix.
So how you find a non-zero number?
For example, we have the entire matrix that contains both zeros and non-zeros.
Correct.
To get the non-zero number.
To gate?
Non-zero.
Go to get?
To get the non-zero entry. We don't have to visit the every.
No, that's, yeah, exactly. That's the point, as I said, that we don't, if you store it like this, if you store a sparse matrix in this form, you wasted, it's exponentially, so the number of non-zero entries is polylogarithmic, right? It's a polynomial function of the logarithm of the size of the matrix. If you fill it up with zeros, then you've got some size. If you don't store the zeros, then you just saved an exponential overhead, both in space and time. You got to call it. So then what you're saying, how do we get it? You'll never get a zero element. Well, no, I shouldn't say never get it. You could get it, but you'll never get more than a polylogarithmic number of zero elements. That's the whole point of the query. So remember what I said. You ask for the third non-zero entry of that column. Of course, it's not zero. Yeah. So that's the point. You want to save on, you don't want to waste time on zeros.
If you expand outwards from the diagonal, meaning if you look down, left, and up, right from each unit of the diagonal, at most there'll be 1 0 in the middle, at most.
Right, but
You end up hitting the last non-zero.
okay, but there will be, I told you that it has to work under permutation.
Yeah.
So what you're saying, like basically the way it has to operate to be useful is that the algorithm has to work under all permutations of rows and columns. Therefore, that thin band that you're seeing doesn't apply under permutation. Yeah. So you can't, if you're going to use it for general purpose, then you can't take advantage of that property. Okay, so that's the idea. Now let's go through what we're solving here. So actually, let me go back for a moment. I'm going to make a key point. It's interesting. So since 1996, Seth Lloyd wrote a paper in Science. We recognized that we were trying to solve quantum mechanics is basically a differential equation. Okay, so it's the derivative of something equals something, and you can think of it as an eigenvalue problem or solving a differential equation. And it wasn't realized clearly until 2009. I'll talk about this. The paper by Harrow, Hasidim, and Lloyd in Physical Review Letters 10 years ago, that if a quantum computer can solve a differential equation, the Schrödinger's equation, it can solve differential equations. And if it can solve differential equations, it can solve algebraic equations. So the idea that we're simulating quantum mechanics, and quantum mechanics is described by a differential equation, why not just use it to solve equations? So that's where the linear equation solver emerged from. But it's amazing. You know, I've worked in the field since early 90s. So, you know, it's funny because I could talk about things and they're obvious now, but because I lived through the period and I never thought of it, things were not obvious then, but now it's an obvious statement. Okay, so let's go to it. So here, the idea is we're solving this wave function as a function of time t. That's it, just a differential equation. But what does it mean to solve? So I just wrote down a set of things that appear in the literature. This is a confusing point for a lot of scientists. Just want to make it very clear. So in the literature, I find 4 different meanings to solving the equation. So 4 different meanings. One is to solve that state. So that's just a vector described by a differential equation and how it evolves over time t. The second one that people refer to is finding the spectrum of the matrix. So if you take your matrix and you diagonalize it, so diagonalizing a matrix is really finding the spectrum. So think of that as a diagonalization of the matrix. The third one could be just find the vectors or the low vectors. So you can use LU techniques or whatever. There's good, I forgot the name offhand, but good algorithms just for finding the lowest ones. Another one, and this is what Feynman was referring to in his paper that launched quantum computing back in 1982, is to estimate the mean of some operator. So, and this will come up again, the expectation value of some matrix with respect to a given state. So those are 4 different ones. I just want to be clear here. So the one in red is the one that we're going to tackle. Determine the spectrum of H for the general problem is, there's a complexity class known as QMA. This one is regarded as too hard, even for a quantum computer. Finding the eigenvectors in the generic case is too hard. And the mean of some operator actually is very important because in my way of defining quantum computing, there has to be classical information out. This on its own, to me, doesn't close the problem. I see this and this together as necessary. And I'll make it clear soon when I cover the linear equation solver. Where does it have applications? Well, once we realize that we're solving a differential equation and therefore we're solving a linear equations, it has applications in chemistry, physics, coupled linear equations, differential equations, machine learning, and so on. Many. I want to be very careful. When I say applications here, they're not proven yet. So I like to be very honest in the discussion. And the honest thing is that this is still speculative. There is no problem that we have managed yet to identify, even theoretically, that a quantum computer would enhance performance. On the other hand, we haven't proved it doesn't work either. So there's a lot of open questions and a lot of very enthusiastic people who are exploring these applications. The theory is very limited. So what's going on nowadays is that companies are buying time on quantum computers because since the theoretical answers aren't clear, they're buying time on quantum computers just to check empirically through running it where the speed ups are and all that kind of stuff. So this is where things are. So these, much to my surprise, quantum computing companies are doing very well. There's no proven use for the quantum computer, but I never expected the fact that we can't prove they're useless is enough to drive companies to spend money to test them. And maybe it will deliver an advantage. Okay, so let's keep going. This picture is meant to give you, again, just to reinforce the view of this continuous time evolution. It's not, oh my goodness. Yeah, so it's one of these, oh yeah, it's one of these PowerPoint problems. It didn't, I write on a Mac, I put it on a PC, and so some of it's messed up. One of the reasons I never use PowerPoint, except this, I'm very embarrassed to be using PowerPoint. Okay, I'm glad that's recorded. You can send it to Microsoft. Okay, so anyway, I'll try to explain what's going on. So this is, I'm going to explain with this picture, and these symbols were supposed to be other things. And the idea is I just want to get across the idea of this Hamiltonian simulation. So let's just think of a physical world, but the physical world is quantum mechanical. So we have an initial quantum state. For the sake of argument, think of this quantum magnet. Every element is a qubit. They interact with each other, and it's going to evolve. And it evolves under some Hamiltonian. That Hamiltonian can be the Heisenberg Hamiltonian that I showed you earlier. And it evolves for some time t. And then finally, the magnet winds up in that state. Okay, so you see, that's just an evolution. And the description all takes place in Hilbert space. These states are. So the magnet starts, evolves under that Hamiltonian for continuous time, winds up here. Then what happens is we have to put it on a quantum computer. So on the quantum computer, when we simulate it on this machine, we make this finite size quantum magnet like D-Wave does. And then we start off with an initial state. That tilde on top represents that it's only an approximate state. So this is machine error on a computer. So a quantum computer has a quantum machine error. That's what the tilde represents. Over here, the computer doesn't work in continuous time. So everybody in computing here and computer engineering knows that there's a cycle on a computer, right? You don't, never continuous time, everything has to be synchronized. So think of T over R as the time for a cycle. And each of these Hamiltonians, H subscript J, is that one sparse Hamiltonian. So that was the case where we color it, so we have each Hamiltonian has no more than one edge to every vertex. That's what's going on inside of here. That's the evolution. And then I need to look, oh yeah. And then what happens is we get an answer. And here, this is the answer within quantum machine error of what the state should be. And this is the answer we get through that approximate evolution. And then we have to work out the error. And then the error is interesting. So when you have a computer and you run it and you get a slightly wrong answer, what do you know? You have an output. And if the output is some double precision representation of a real number and it's slightly off, you just take the correct answer minus the answer you got, take the absolute value, and that's your error. On a quantum computer, it's much more subtle because these are states in Hilbert space. So it turns out we need another distance measure. For anybody who wants to look it up, it's known as the Fubini-Studi metric. So this is the error. So this is kind of how you think about this continuous evolution. Okay, so we've got, this is kind of representing how it's going to work with a Hamiltonian simulator. And I just wanted to give you an idea of the gate, just to show you how it works. So suppose that we know we're going to execute this on a regular quantum computer, and we have that one sparse Hamiltonian. Well, we have some Hamiltonian. I'll just show you. Like if we take any Hamiltonian and build it out of gates, we have a way of representing it in a circuit. So this could be a particular Hamiltonian. This is not one sparse, but I'm just showing you, remember S was T squared? And so I'm just trying to show you here that we have a way of writing a circuit representation for everything. So when we study the complexity of this, we're able, in every case, to map it to circuits. And remember how we count time? We just cycle, 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 just count the number of gates through the cycle. Okay. So that's the Hamiltonian evolution. Now let me get to the point that relates us to machine learning. And this is a 10-year-old paper. So Aram Harrow, he's now the head of theoretical physics at MIT. To me, he's a baby. He's just, probably not even 40 yet. So I know a lot of you are younger, but to me, anybody under 40 is a baby. So there. Avi Natan Hasidim has moved on to a different field. Seth Lloyd, you'll see his name a lot. He wrote many of the papers, including the 1996 science paper that kicked off the whole quantum simulation field. And so this paper is called Quantum Algorithm for Linear Systems of Equations. So I want to spend some time on this because this is one of the two most highly valued algorithms in quantum computing today for applications to things that you might be looking for. So let's go through. I'm going to read, I know it takes time, but I'm going to read through the abstract, and I'll write some expressions on the board so they're clear to you. So solving linear systems of equations is a common problem that arises both on its own and as a subroutine in more complex problems. Okay, and we'll talk about why it's important in machine learning soon. Given a matrix A and a vector B, find a vector x such that AX equals B. So what they're saying, they're describing in a way that I think you'll find obvious. So they're saying, okay, so this is it. So here's a matrix A, a vector x, a vector B. You know B, you know A, find x. And you've done that since you were kids. Okay, so what you didn't know is it's a hard problem. You know, the teacher might have told you it's straightforward, taught you how to do it, but now you know better. Now you know it's actually computationally complex. So one day in the future, every kid will go to school with a quantum computer, and they can solve it efficiently. That's the hope. Okay, so find that. Now, we consider the case where one does not need to know the solution x itself, which is reasonable because you're trying to find the solution x, so it's kind of a no cheating condition. You have to find the answer, and you can't know the answer in advance. But then one does not need to, need to know the solution x. You don't need to know x, but rather an approximation of the expectation value of some operator associated with x dagger mx.
I think it is to change the batteries from x, right?
What?
The batteries of the one that was in the pocket.
If you have a backup, I don't understand. But I can keep talking, right? Yeah. What if they both go? It's possible. Non-zero probability. Okay, so let me write down the next expression. So what they're saying is not find x. They're saying calculate x dagger. So I'll write it as x transpose to make it clear. Mx. You see what they're saying? So the way as a kid you would have got the problem is they're saying, given a linear equation, find x. We don't want to find x because x would be, remember I told you about polylogarithmic? But x is huge. Every operation we do should only be a polylogarithmic size. So you want to give that one back? So we don't want to do that because that would make the problem intractable. But instead, given this and given a matrix M, find this. You see? So like if you think of, suppose that we took 3, 1, and then the matrix, I don't know, 1, 2, minus 1, 5, and then we took, this would be 3, 1, then we would just go through calculation. It would just be, it's a quadratic function. So it will just give us a number. You understand? So just multiply, blah, 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 go through it. So the idea would be to find that answer. So we want to do it for some m. And so the goal is not to find this, but to find this. Let me go back to a comment I made earlier so you're clear on the point, because I'm making an important point, I think. I made a comment here. I said, the way that the linear equation solver is often expressed is analogous to this. That wave function psi as a function of t is equivalent to that x. And then I said to you that in my way of thinking, this can't be separated from this. This is analogous to that. See? So in my way of thinking, as long as it lives on a quantum computer, you have an answer to question. This one goes back to Feynman's 1982 paper. And so we do this and we do that. I'm going to wake him up. Gibber? Gibber? He's sleeping all through my lecture. I don't like it. Can you sit up? It's okay. It just bothers me if you sleep. All right. Okay. So let's go through. Okay. So that's the idea over here for some matrix M. Then they're also saying they're putting conditions on for when quantum can help. So here, in this case, when A is sparse, remember what I explained sparse was? No more than polylogarithmic number of elements is non-zero. Its size n by n, that's the size of the matrix, and it has a condition number kappa. So let me explain the condition number. Okay, so think of this. If I diagonalize a matrix, so if I diagonalize the matrix A, then I get eigenvalues. These eigenvalues are the spectrum, right? That's the word for it. So we have a spectrum. Now I can think of lambda max over lambda min. So these eigenvalues I'll just call lambda. And then lambda max over lambda min, I'll call that kappa. And the idea is that lambda max over lambda min, the kappa value, cannot grow more than polylogarithmically size of the matrix. This is really important because you can then ask the question. So if anybody here do linear equation solvers, you know about preconditioning? No, nobody does it? Okay. So when you do solvers, there's a preconditioning step. The idea is that the condition number has to be handled. If you've ever done stiff equations when you solve numerically, it's a problem. So what's happened is there's a very strong condition on the condition number that I'll get to in a moment, but it's very important. This key point might make it inapplicable to most problems. Then they say the fastest known classical algorithm can find x and estimate this in time scaling roughly as n root kappa. That's the condition number coming in. Here, we exhibit a quantum algorithm for estimating x dagger mx, which is a polynomial of log n, you see, and kappa. So that log n is an exponential reduction in the cost of the algorithm using a quantum computer. That's the key point, whether that holds. If that holds, if this all holds, then it's a game changer for all of science. Not just machine learning that, but everything, if it works. So this is the thing. There are a lot of caveats. And so one of the challenges in the field is to identify the problems for which these conditions are met. And then they do it, they have that log n. For small values of kappa, which have to be polylog in n, and this is a problem. How many problems have a condition number that are polylog in n? We prove that any classical algorithm for this problem generically requires exponentially more time than our quantum algorithm. So they prove an exponential speed up for a well-defined computational problem that might not have a use case. It's the best take-home message for it.
Why is it related to the eigenvalues maximum?
Why? Because
The eigenvalues. Why is it? Why are they important? The maximum.
but that's in the details of the algorithm. I mean, so you're asking where in the algorithm does the condition number pop up? Yeah, I'd have to go through the algorithm, which I won't be able to do. Yeah, so at this, I'm doing the high level, just going through that, but yeah, I won't be able to go through it. Okay, so let me go on. Yeah, okay, so that's the key point there. Now let me go through. First I'll tell you why it's important, and then I'll go through what the danger signs are. So why do we care about it? And now, as I said, it's important in many fields, but this is not a complete set. But if you're interested in machine learning, this is where linear equation solver comes up. What's interesting to me actually is that when I go through machine learning algorithms, they're often kind of very mixed together, not easy to separate. Like if you think of structural programming, there's a way of separating things out, and most of the stuff is put together very quickly. And so one of the things that I do nowadays to get funding for my group, keep my students going and all that, is on the side, not their PhD projects, but on the side is we're trying to get very quick at being able to take existing algorithms pull out the part that's relevant to such quantum algorithms, figure out it's not easy to do. So I'm telling you that it's important, and not many people are good at doing this. It's not a big intellectual challenge, but it's needed. So these are things that we do. One is we fit a model to a data set. So you write down a simple model, you have data, and then you fit to it. It could be climate modeling, it could be predicting the next election, whatever it is. And this is often done by linear equation solver. You don't have a perfect fit, and then you fit the model. Linear regression is a type of that. So linear regression techniques, most of you know. If you don't, it's easy to look up. Uses linear equation solver. Regularization, which is regression with a constraint on small coefficients. So you restrict that. There's principal component analysis, which is taking a big data set, doing a dimensional reduction. It's kind of like taking a table and deleting columns and rows. And that's done often by matrix factorization. One example is the singular value decomposition. There's, in natural languages, latent semantic analysis, also uses matrix factorization. Recommender systems. So this is the kind of stuff that Amazon would use. So you go, you buy a few things. When you buy a few things, Amazon has a sparse matrix about you and uses a sparse matrix to be able to predict the next element. By the way, the principal component analysis makes use of sparseness conditions. So it assumes, like, in order to use principal component analysis, it has to be sparse. And deep learning also makes use of linear equation solvers. And so these things all have built within them linear equation solvers and sparseness conditions. And remember I told you that in physics, our matrices often have this property, they're sparse. And so it's very interesting how that comes up. It also comes up in these systems that we can often make use of sparse matrix stuff. So this is where possibilities exist. I'll just tell you a little story about the recommender system, which I find very interesting. This is, there's a person, Yuan Tang. I met her, I invited her to a meeting in Montreal a couple of months ago, met her for the first time. So she's 19 years old, second year of PhD at University of Washington. And so she did her, started her bachelor's degree at University of Texas at Austin at 14. And her advisor was Scott Aronson, who does a lot of stuff on quantum computing. And then she finished when she was 18, but when she was 16, she was posed the problem about recommender systems, and Scott was conjecturing that there was an exponential or sub-exponential separation between the classical and quantum algorithms. And so she basically found a classical algorithm, assuming sparse matrices, that got rid of that sub-exponential separation with the quantum algorithm. That was out last year. That was published last year. She had a couple of papers out. One is sole authored, and it was very nice. But the story is interesting because it's a case of a 16-year-old getting a well-posed problem and just plugging through, knowing what was going on, and a sole author paper, not with her supervisor. She just, took it, solved the problem, found the classical algorithm to close that boundary. So when I'm telling you that it's not obvious, that it's not obvious that whether the quantum algorithms offer an advantage or not, it's really hard. And she solved the problem many people were stuck on. So I think the lesson is you got to find a 16-year-old to come in and pose the problem clearly, and they can solve it. So that was it's kind of a very neat result done last year. And then she came over, so she's 19 now. So she solved it at 16, wrote the paper up later. She gave a talk at our invitation-only meeting in Montreal, and the best talk there, very clear, really good thinker. So this is the kind of thing that's going on, but you really need smart people to jump in and figure out what is the quantum algorithm giving you, and then they often do things that are now called quantum-inspired algorithms. You look at how the quantum algorithm's done, and then you jump in and use those techniques in a probabilistic way. Okay, so that's kind of motivating the whole thing that we're doing with this linear equation solver. So it underpins a lot of the machine learning. Now, let me go through what this does. So I won't touch the condition number restriction you're asking about, but I'm just going to spell out roughly how the algorithm works, and then I'm going to show you what the caveats are that have to be tested to decide if it's applicable to a particular problem. So the first thing to note is that it modifies KIT-F's eigenvalue estimation algorithm for Hermitian A. So we assume for the equation solver that that matrix is, Hermitian is self-adjoint. This condition, complex conjugated matrix transpose, that's hermiticity. Okay, so we assume it. It turns out you don't have to. If you don't have a self-adjoint matrix, you just double the dimension, and then you would just do, you would put A here, A dagger here, and a big matrix of zeros here and here, and then you just double the dimension so you're able to make it. So it works by doing that, but it's trivial to overcome the problem. Okay, now what we have to do here is we have AX equals B. Okay, so we have, remember, AX equals B, but it's not going to be the case anymore. Now we'll have A, and I'll put a hat on top to indicate an operator. Then we have the state in our quantum computer, so it's a vector, equals B vector. Okay, so the problem now becomes solve this equation, but we put it inside the quantum computer. So so B is now written in the quantum computer. So that's what they're saying here. Prepare and inject B as an input. We've got to keep track of that. The problem is, remember that if we write B as remember I told you all the work we went to on the matrix to keep it polylogarithmic by doing a graph. The same concept exists here. We can't write in the vector B if the vector B is length n. It's got to be kind of sparse, you know. So it could be mostly zeros, and we write it carefully, or there could be a simple algorithm to generate the B's, but it's restricted. The only B that we could write in the system is a B that takes more than polylog space and time to write in. Do you get it? And that's important because if that fails, don't use this. Okay, then what we do is to approximate the vector B in terms of the eigenbasis of A. But we can't diagonalize the matrix. So then there's a lot of tricks that go on here, but we have to basically, when you change the basis, this is a rotation in Hilbert space. So you have your vector in Hilbert space, rotate it. So we execute some rotation using, motivated by that KIT-F algorithm. And so we rotate it to a new basis. And that comes up by essentially recognizing AX is B is the same as X equals A inverse B. If A is invertible, I can put an A inverse on that side. That A inverse is something like a rotation. So they do a rotation in Hilbert space. And they have the basis with the eigenvalues. Aisha, this goes back to your question that the, where does the condition number come in? It turns out that if you have a big condition number, then when you write the rotation, you have big rotations on some and small on others. And that's where the problem comes in. Okay, and then they show that for an n by n matrix, n is the logarithm. So capital N is the size of the matrix, little n is the logarithm. So they're showing that if you have an n by n matrix A, and little n is the log base 2, then it's little n times log n steps. It's highly efficient. They could do the whole thing in big O of that. You guys know big O? Okay. And then the result of the quantum algorithm is, the result of the quantum algorithm is eigenvalues and eigenvectors, but it's still written in the quantum computer, and then we do controlled rotations on B, undo it to get X. So there's a set of steps I don't go into, I don't have the time, but we get the result X. So this, under those caveats, is highly efficient, and we have the answer X to the problem written in a quantum computer. But we can't read it, because if we read it, it will take an exponential number of steps. Okay? So we can do all that efficiently, but if we read the answer, we just undid all the benefit of doing quantum computing. That's why Harrow, Hasidim, and Lloyd point out the need to go to that next step, right? That you don't want to read X, you want to evaluate a quadratic function of X. And so that's the next point that they go on to. That's in their abstract back here. It says, of some operator associated with X for some matrix M. They word it very carefully. They say for some matrix M. It turns out that we could generate X efficiently, do everything efficiently, but if you pick the wrong M, that won't be efficient. So you have to check not just the efficiency of the quantum algorithm to generate X, but also the efficiency of the quantum algorithm to evaluate that quadratic function. That's important in all analyses. So we study the application of the linear equation solver, we have to check both. Okay, so this is the famous paper by Scott Aronson. I don't know if people know Scott Aronson. He writes a blog called Shtetl Optimized. He's a very funny guy. Just, you go to his talks. You should get him out here. So if he gives a talk, he's always, everybody's laughing all the time. I wish I could do that. So he's doing that, but he does it. He wrote a blog about it, and this is Nature Physics. And Nature Physics asked him to write an article, turn his blog into a Nature Physics paper. For those people who care a lot about publishing good journals, this consider a good journal, and having somebody knock on your door and say, please, can we reprint your blog in our journal? That's a career maker for some people. But he's a very good writer, and people always want his stuff. So he called this is an article about the Haro-Hasidim-Lloyd paper. And Scott at the time was at MIT. He was in computer science. And Haro-Hasidim and Lloyd were all in physics and mechanical engineering. So they're all the same place. He knows it. They're not fighting with each other, no criticism. But he just wrote the blog called Read the Fine Print. And Read the Fine Print has a nice message because it's not saying Haro-Hasidim and Lloyd made a mistake. He's saying for all the people who are getting too excited by it, read the fine print in their own paper. Pay attention to everything they wrote, not just half of it. So he writes here in that commentary, new quantum algorithms promise an exponential speed up for machine learning, clustering, and finding patterns in big data. So that fits exactly with the people who are here that want to know about machine learning. But to achieve a real speed up, we need to delve into the details. And remember I told you, so Scott was he moved to University of Texas at Austin. He was the supervisor of Yuen Tang, the one I told you who solved that big problem at the age of 16. And so, he was guiding her on some of these issues. And so he goes on, for 20 years, quantum computing has been catnip to science journalists. You know what catnip is? There's a cat. There's a kind of food that has a bit of a drug in it that's natural, and cats go crazy over it. So if you have a catnip, they go crazy. So he's writing in that colorful way. Okay, he goes, and he says here, HHL, that's the Haro-Hasidim-Lloyd, attacks one of the most basic problems in all of science, solving a system of linear equations, and then he describes it. Okay, so you get the feeling. Okay, so here he writes the paper, and then there's a very nice box that it's called 4 caveats. So these are the 4 things you have to watch for in that algorithm. Okay, let's go through them. I know it's hard to read, so I'll just tell you the key points, and you can always look them up later. Okay, this is the vector b. So remember, we're going to solve ax equals b. There's the vector b, and it says the vector b somehow needs to be loaded quickly into the quantum computer's memory. Quickly is what I told you has to be polylog. So it has to be polylog in time and polylog in space. I keep saying polylog. I think I've explained it, but if I say a word you don't understand, just let me know and I'll re-explain it. Okay, so that we can prepare a state, that's the ket, so the quantum state is the sum, and the i's are the eigenbasis of the A vector. So it's what I said back here, prepared in that eigenbasis. That's what he's writing. Whose n amplitudes encode the entries of B. And back to Aisha's question, if the condition number is bad, then these numbers will have bad ratios, and you wind up with an exploding number of bits that you have to keep track of. Then he goes on, a lot of stuff not important. He says, at least in theory, this can be accomplished using a quantum RAM, a memory that stores the classical values VI, and that allows them all to be read in at once in a quantum superposition. So there's a paper by Seth Lloyd and others on quantum RAM, quantum random access memory. There is a criticism of that too, so I just want to be a little bit careful that at least in theory it can be accomplished by that. There's some caveats on the quantum RAM. But the quantum RAM is meant to get around the problem to read in all the B's at once. But B has to be relatively uniform without a few values of B that are vastly larger than the others. This is the condition number statement. Okay, so it won't work if the elements of the B that you're using in your linear equation solver vary too much. So it can't change by a lot. And then, okay. And there's other caveats. I won't go into everything. He does say what I said before. Remember, if there's an algorithm to prepare B, so if there is a way to write a quantum algorithm to prepare B efficiently, then that's okay too. And then you don't need a quantum RAM. But he says if preparing B already takes n to the c, so that's Pauli n steps, then the exponential speed up of HHL vanishes at the very first step. So his n is not the same as the HHL n. Okay, so that's the first warning. Make sure your B can be written in the quantum computer efficiently. Second one, the quantum computer has to be able to apply the unitary transformation of the form e to the minus at. So remember what I told you about Stone's theorem? So A is the matrix here that we're trying to solve, and we exponentiate it. That's the unitary matrix. Remember? Okay, so this is, by making that statement, it says that the quantum program has to be, the quantum program generated by that A. That A is effectively the Hamiltonian. So the quantum program generated by that A has to be efficient on the quantum computer. Once you understand the idea that that's a Hamiltonian and a Hamiltonian generates a unitary, then you understand it's a trivial statement. It's just saying the quantum program has to be efficient. And then it says if the matrix is sparse, and it defines it, but I defined it more carefully for you. And if there's a quantum RAM that stores for each I the locations and values, so this is the oracle I told you about, you know, the way to call it, then it says that it's known how to execute it. Again, though, if applying e to the minus at takes n to the c, so it's Pauli time, for some constant c, then the speed up disappears. So you have to check that the program, as the problem size gets larger, will still be executable efficiently. Now, let's go to number 3. So number 3, the matrix A isn't just invertible. Remember I told you here that this looks like A inverse over there. So it has to be invertible, but robustly invertible or well-conditioned. So the condition number comes in there. And this is the condition number I wrote over here. So the condition number is the ratio of the largest to smallest eigenvalue. And then what they're saying, if kappa, that condition number, grows like n to the c again, polynomial in n, then the exponential speed up is gone. Okay? So we have to check the condition number. And then finally, we can't read x. So I explained all that to you. Okay? So x is not in the classical world. It's on the quantum computer. Reading it shouldn't be done. So he says, when HHL is finished, its output is not x itself, but rather a quantum state, and he gives the size. And it approximately encodes the entries of x. And then he goes through here. So you want to calculate that quadratic function. And he says, as an example, for example, the locations of any extremely large entries of x, or the approximate value of an inner product, or whatever. But learning the values of any specific entry x will in general require repeating the algorithm roughly n times, which would kill the exponential speed up. So any trick you want to do to learn what x is will be exponentially expensive. Okay, those are the 4 caveats. Anybody here work with linear equations? That'd be nice to go through an example. Anybody here do it? I talked to people over lunch who are doing AI stuff, but you want to talk about, do you use a linear equation solver?
Okay, we don't use solvers, but a lot of things are linear in nature, such as convolutions of linear products and a lot of things. But implicitly, these things are being used somewhere.
Right.
Sort of in my work, for example, it's abstracted away. So it's not that.
No, yeah, you're saying exactly what I want you to say, which is all bad news, but you're right. Okay, so that's what I hinted at lunch, but now I'll go on to the point. So you're my test going on here. Yeah, you're exactly right. So you're using the algorithms, and the details are tucked away in the package. Exactly. This is the problem I'm talking about. So what you're doing, then let's say you and I have another conversation. You say, okay, I'm using a linear equation solver. It's tucked into my algorithms. Can this quantum algorithm help? And I go to you and I say, okay, let's talk about your linear equation solver. Okay, how compressed can we make B? This part you wouldn't worry about. I would be testing the efficiency of the quantum algorithm. I want to know the condition number and how it scales with the size of the system. And I want to know what would be the quadratic function that you evaluate at the end, which you do. Okay, so you get it. You don't have the answers for those. Are you looking them up? No. Okay. So you don't have the answer. And I talk to many people about it. So I'm doing work on this. I do some consulting, etc. And this is the conversation I have with everybody. So you're exactly, very respectable, just like everybody else I talk to, in that the answers are not clear. And I'm not an expert on the algorithms. That's where I told you with Yuan Tang coming in at 16 years old, she looks at it, she was able to connect both. So she could go to one and say, I understand how the software works, what the requirements are at the various levels, and I understand the quantum algorithm, and she combines the two. And so for me, I don't find it so easy. And my students don't find it easy. But this will come, tomorrow we'll do a different algorithm, but since I've understood you're looking for applications, I'm telling you, it's a key application, is to be able to go through, so if you get good at that, if you can go through and say, where is the linear equation playing a role in my software, and how much can can it be pushed to meet those conditions or not? If it can meet those conditions, then you'll have discovered the first use case for quantum linear equation solver. And there's much more caveats here, because again, when we do it, the polylogarithmic is we're dealing with worst case. And I told you that the typical need is typical. Typical case is what we're looking for. So if I tell you this and I say, like he says here, the exponential speed up of HHL disappears, so you got the idea. They're doing complexity theory outside of this too, right? Yeah, okay, so you know complexity theory. So when he says this, exponential speed up disappears, what does he mean? Disappears in the worst case, the best case, the typical case? Average case? Yeah. I'm sorry?
It has to go away once you are.
Why do you say the average case?
The average case.
Yeah.
That's kind of like the intuitive answer.
What?
That's kind of like the intuitive answer.
Yeah.
Whenever you do it, it has to go away.
Okay, so you're saying it for the right reason, which is you're in the industrial world, right? No, you're doing your PhD in the facial recognition, that's it. So when you're doing it, you're solving a real problem, right? So when you say it, the intuitive case for you is what is useful for your problem. That's not the case here. So when Aronson's doing it, he's a theoretical computer science. What makes sense for him is to prove a bound for complexity, right? So if we go back to, so that's why I'm setting you guys up for questions. But when we go back to here, and this is what Gibran made me clarify, which was good, these are the complexity classes, right? So this says these problems are solvable efficiently on a classical computer. These are solvable efficiently on a quantum computer. These are verifiable efficiently on a classical computer. What makes that boundary? So just because it's efficiently verifiable on it's not efficiently solvable today doesn't mean we won't find an algorithm tomorrow that will cause a collapse, right? So going back to it, in your case, intuitively, when you're actually using algorithms for practical good, you're saying, well, I just want to know, will it work on the average, and I call it typical. And then, but instead of that, in this sense, when you do these complexity diagrams, and don't forget, this came from Aronson's course at MIT. So I took it from him. When they do this, they're proving everything for worst case. You get the point? So when I go back to here, this is a key point. When I go back to this statement, he says, the exponential speed up of HHL disappears. Does it disappear in the worst case or the typical case? It disappears in the worst case. So when he writes all this, there's a caveat on the 4 caveats, right? He's writing all this and he's saying it disappears, but then there has to be a caveat on that. Maybe you don't care if it disappears. Maybe you only care if it works for you. If it works for your problem and nobody else in the universe, doesn't matter. It worked for your problem, and the case where it disappeared didn't come up. Maybe that happens. So you have to think carefully about it. But these are the issues that are coming up in trying to translate the abstraction of quantum algorithms to real applications. Now, I'm a pessimist, so I think after all the work, we're going to discover they're useless. But just because I'm a pessimist shouldn't stop you. I have to tell you a story. I was doing consulting about 3 years ago. So when you do a consulting report, they get me on as a lead of a due diligence team. So my job when I do consulting is they'll say something about a quantum computer, a quantum algorithm. They want to invest in a company. So they want to invest. And then if I get hired, as lead of technical due diligence, I can pick a few of my friends, pay them too, and together we make a team and we write about the technology. And I always write a bad report. So if you start a company, don't get me to do it because I always write why it won't work. The first time I did it, it was very funny. I wrote it, and it was a investment scale, $50 million. And I wrote it, and I said why it won't work. And I went through it. And they invested. And then I asked, like, why are you investing? And the answer was, there's something known as the Gartner hype cycle. Have you heard about this? Yeah, you know this, right? So there's the Gartner. I didn't know before that, so I'll show you what goes on. I forget the terminology, but it goes like this. It goes up, down, comes up like this. And so the Gartner hype cycle has this hype level, and then it somehow, there's this falling, there's like I forget the word, it's something like plateau of despair, and then there's this levels off to some feasibility. So the Gartner hype cycle works like this. It says that when you get a new field, invisibility cloaks, cold fusion, whatever, all these things, there's a hype level that goes up, and then it reaches the peak of hype, and then it comes down as it becomes more realistic. It doesn't just flow this way, it can flow backwards too. So, something can get hyped and then fall back down there. But if it goes through a promising technology route, it'll get hyped. Then people get more and more despondent. And then when it reaches the plateau of despair, that's where everybody gave up and it can rise. And the point is that investors believe that it's not going to hype, and then deliver. It will always get overhyped and it will fall off and then it can rise. And so when I put in a negative report, they told me they're very happy because they think they're there. So if I write something negative, then it means that they don't want to invest here, they want to invest here. So that's the point. That's what I learned. Pardon me? Yeah.
All I said was it only goes up from there.
No, it could go both directions. Yeah, it can also come back. The arrow of time is not fixed. Yeah, it can go back. Everybody can be disappointed, it can still fail. But the investors regard that like a coin flip, So when you do, like currently, the rate of return on quantum computing investment is 100 to 1. So if you want to, the investors go in, they only need a 1% chance of success for their investment to break even. That's how they're working it right now. Okay. So when it's down there, if they think there's a 1% chance it will go that way, break even level. So that's where it is. So I just told you. So I'm a pessimist, and the pessimist that I am doesn't stop the investment in the field. What are we doing for time? 10 more minutes? Oh, 20? Is that clock wrong? Do you want arithmetic or just subtract? Okay, nap, that makes sense. Okay, yeah, so I don't remember what else I prepared. Oh, yeah. So I think, let me just, okay, so I kind of wrapped that point up. That's all I wanted to say on the linear equation solver. Anybody have any questions about that? No. Okay, that was the amplitude amplification. But you're covered a bit, and I don't think I want to go into it. The hidden abelian subgroup. Yeah, that was the Shor algorithm. This gets, okay, let me go back. I'll just talk for a few minutes on it, but I can get into the technical details, but I don't want to wear you out with that. So I'm going to go back for a moment. And then I mentioned this eigenvalue estimation problem. Actually, I'll tell you a short story about that too. It's kind of interesting. So Peter Shor worked at AT&T, and he came up with his algorithm in 1994. I remember this. I was living in Australia, and the news traveled all around the world. So what happened was Peter Shor figured out his his quantum algorithm for factorization. And this changed the whole field of quantum cryptography completely because, all of, not quantum, the field of cryptography, because all the beliefs about security changed. It basically was this problem that Shor's result essentially established this class. And the idea that factorization was safe because it's here and it moved into there meant that a quantum computer could break it. So that's what Shor did. And then what happened was so then what happened was Shor came up with that in 1994. The word spread. I was in Australia and I was talking to some mathematicians, analytical number theory people who work on these kinds of complex problems. And they told me what was going on, that Shor agreed to go to the analytic number theory meeting somewhere in the southwestern US. And the problem with Shor is he doesn't like to write papers, won't write them, but he'll tell people. So when he solved it, he went and told his boss at AT&T, and his boss then told people saying, Peter Shor solved the problem. But his boss didn't understand the solution, and Peter Shor, the only way to get him to do it is you have to invite him to a meeting somewhere, and he doesn't like to travel. So that was the problem. Then what happened was when the news spread to Russia, Alexei Kitaev, who I mentioned earlier, heard the result. So unlike people like me who fretted and thought, how are we going to find out how Shor did it? He doesn't write papers, and he solved the problem. So we're all trying to figure out how to do it. And Kitaev was a genius in Moscow who just decided, once he heard it was solved, he tried to figure out how it was solved. So then he worked out his own, he knew there was a solution, then he figured it all out by himself. In fact, his algorithm was better than Peter Shor's, so it was good that he was left alone. He did it. His result was really good. Kitaev is another guy. He doesn't write papers either. It's very funny. It never survived in Pakistan, where I think you guys have to write papers all the time. So, and then Kitaev, by the way, doesn't write papers. I was at a meeting in Japan back in 1999, I think, and they got Kitaev to come out to talk about his solution. There's Shor who solves and Kitaev who solve, and neither one liked to write things up. So then I remember Kitaev came. He came to the meeting. I think he was meeting with John Preskill. Caltech offered him a job right there, so that was it. So he's at Caltech, and the fact that he did it on his own was very important. So was a key point in getting to Caltech. Okay, and get the message here. The really good people don't like to write papers. Okay, so don't feel badly if you don't. So then the way the problem works ultimately can be boiled down. So Shor solved factorization. The ultimate guts of it are just finding a hidden subgroup, and that relates to these cryptography-related problems. So RSA, you know RSA? Yeah, so the RSA algorithm, type 1 crypto, which is the most secure one in the United States, relies on elliptic curve cryptography, which I'm proud to say was a Canadian invented algorithm, not me, but somebody. Pell's equation, and so on. So there's a set of different algorithms, and I didn't write it properly. Should be considered an abelian subgroup G here. So there's an abelian subgroup G, group G, abelian subgroup H, and a set X. And then I just wrote down the technical details, which I won't go into, but there's some hiding function that hides this. This is essentially, this relates to the periodicity of encryption. So when you encrypt things, the things are breakable by periodicities. This is the mathematical representation. Sorry, there's a typo, it should be oracular. And so this is the mathematical formulation of the hidden abelian subgroup. This is the one that's hard classically, so the number sieve algorithm is the best, is the bottleneck and the best we can do, easy quantumly, and it includes all these different algorithms. So this one that was used by Shor is at the heart of the linear equation solver. So when I mentioned Kitaev, it's using the same hidden abelian subgroup. And I won't go into it, but Gibran said for those who are taking his course that he'll teach the Shor algorithm. It's got that component, and I kind of put here what's going on. So I'm going to finish by just telling you about Shor's algorithm on a high level, and then you can figure out later what's going on. So there are 3 steps in Shor's algorithm. This one takes a set of qubits in the 0 state and applies Hadamard to each one, and I'll explain. Then this is known as the modular exponentiation step. So this is known in number theory. And then this is the inverse quantum Fourier transform, which is the guts of what Kitaf and Shor figured out. So in here is the real guts of what's going on. This was actually known before by Simon. Something known as Simon's algorithm was a precursor. And I talked to Peter Shor about this. So he was on the program committee of the conference where Simon's paper got rejected. And he learned it through that, and then he used it here. But he's very open that, you know, he told everybody he was using Simon's algorithm. But nowadays, nobody remembers Simon's algorithm, and they know his. Okay, let me just explain a little bit so you can see what's going on, because it looks like just a bunch of symbols. So this one, remember, this turns 0 to a superposition of 0, 1, 0 to a superposition of 0, 1. When you apply a tensor product to Hadamard's to all the qubits, this has the effect of making a superposition of all numbers. So if we had 3 qubits, we have the numbers 0, 1, 2, 3 up to 7. This would turn it into an equal superposition of 0, 1, 2, 3, 4, 5, 6, 7. So this is how we make parallel computing in a quantum computer. So if you do parallel computing on a computer, existing computer today, you have parallel processors. This is the equivalent in the quantum computer. This parallelizes everything. So after this point, it's a superposition of every input going in. This part is actually the classical algorithm about squaring. So we have to, this is from the Wikipedia page. It's actually a poor representative diagram, but the idea here is that, that exponentiation by squaring is a very quick classical way of evaluating some number. So I want to take 2 to the power of 7. I can take 7 equals 4 plus 2 plus 1. Then I get 2 to the 1 is 2, 2 to the 2 is 4, and 2 to the 4 is 4 squared is 16. And then I can just multiply those numbers. So by using this idea that when you square a number and you square again and you square again, that's what's going on here. And then these are simply, these controlled operations are simply, these are all the bits. You have a bit representation of the number, and then there's the highest bit, next highest bit, and so on. And so there's stuff going on here. But basically, if you learn the modular exponentiation rule, then what these gates are doing, when you see a controlled rotation, these are if then else. Okay, so let me try to be clear. When I see this, I'm getting good at reading these programs, because when I see this, I think that's quantum parallelization. When I see this, I see if then else statements. If then else, if then else. These are all related to bits. And if you go through modular exponentiation and you bear in mind the if then else rule, then you'll see, you can quickly understand what's going on there. And then the inverse quantum Fourier transform is like the fast Fourier transform method, but executed on a quantum computer. And this is where a lot of the speed up takes place. So you have your parallelism, then you have your if then else on everything, and then your inverse quantum Fourier transform is going from the computational space to a dual space. And basically, the effect of this is that all the wrong answers, not all, most of the wrong answers interfere and kind of cancel out in a way that they don't have a cost, and because you don't need to make your computer big enough to hold all those cases. And so the inverse quantum Fourier transform basically causes interference, and then you have your measurement step, and then that's the output to the computer. So that's the element, and this construction, this phase estimation stuff is then inherent in many other algorithms. Okay, so I think I'll close on that, and then tomorrow morning there's the problem solving session. So I'll pick some things today, and they don't do it, do they?
It's up to you how you want to run it. Do you want to run the problem yourself? That's fine. Or if you want to give them something to do.
Yeah, I'd rather that we just did it together. It'd be hard to do it on your own. So I'll just come up with some cases, and then we'll just solve them together on the board. And then I'll do the quantum annealing variational quantum eigensolver tomorrow afternoon. Done.